Okay, welcome everyone to Physics 390 Class 25. This class is on time-dependent perturbation theory. So in this class, we're going to look at a case where we have an extra energy to a system which depends on time. So an example of this would be the energy associated with an electromagnetic wave, because the amplitude of that wave and the energy associated with that wave depends on time as it passes a given position. And we'll see a couple of techniques. We'll treat two-level systems, and we'll see how the perturbation theory works when the perturbation is time dependent. And this material comes from chapter 11.1 of our textbook. Okay, let's take a look here. So as an overview, if we have a time-independent potential, V of R, so it depends on space but not on time, it produces states with constant probabilities, Cn squared, for the different energies En, the different eigenstate energies En. So a typical wave function would be psi of R and T is the sum over n, Cn weights, psi n of R, where these are the eigenstates, and then the time-dependent oscillation factor, e to the minus I ENT over h bar. So even though this is a combination of different states, the probabilities Cn squared remain constant in time. So there's no chance for one state to become more likely or less likely. They all just oscillate in time according to their own time dependence. But it's not like you could start in, say, all in C1 and then have some probability move over to C2. The probability is constant for each. And that's because we have a time-independent potential. So to see changes in these probabilities Cn, which would represent transitions between states, these eigenstates psi n of R, we need to introduce a time-dependent potential V of R and T. Okay, so a time-dependent potential V of R and T. And that has a chance to drive transitions between these states. So we can treat small time-dependent terms with time-dependent perturbation theory. And we'll look at that in just a second. So why would we want to do this? Well, as I kind of alluded to earlier, a big motivation is the important case of emission and absorption of radiation, that is electromagnetic waves, by an atom. Atoms move from energy state to energy state and emit photons, and that's a huge part of atomic and solid state physics, which quantum mechanics wants to, or is supposed to, treat very accurately. So we'd like to be able to understand that process better. And so we need transitions between these states, not just constant probabilities in these states. So time-dependent perturbation theory is very helpful with that. So to keep this as simple as possible, we'll work with a system with two eigenstates, psi A and psi B, okay, as opposed to the infinite square well, which has an infinite number of states, or the hydrogen atom. We'll just assume we have two eigenstates, psi A and psi B. The mechanics of this can be extended to more than two states, but it's the same idea. So this will give us just a simpler look. So we start off with a wave function in the without the time-dependent term, which is just the first eigenstate psi A weighted by Ca plus the second eigenstate psi B weighted by Cb. And then that's at time 0. So at time t, we get the same thing, except the psi A, Ca psi A will be multiplied by the wiggling exponential factor associated with the Ea associated with the eigenstate psi A. And similarly, the Cb psi B will be wiggling according to e to the minus I ebt over h bar. Okay, So this is, again, this is without a time-dependent perturbation. So it's an example of this first wave function here, whether we have two states, CA and or psi A and psi B with CA, CB. So it's just an example of this for two states. And then with two states, we know the total probability should be 1, and the probability of state A is CA squared. The probability of state CB is CB squared. So those must total to 1. Okay, so this is kind of our setup. Okay, so let's see what happens when we introduce a time-dependent perturbation. And first, we're going to do it exactly. The results on this page will be exact. And then we'll look at a approximation for a small perturbation, time-dependent perturbation in just a minute. So if we apply a time-dependent perturbation H prime of t to the two-level system we just talked about, we can express the solution in a similar way to what we had on the last slide, since psi A and psi B are a complete set of eigenstates. So any wave function can be expressed as a linear combination of psi A and psi B. So notice the only difference between this and the previous slide is that now CA is a function of time and CB is a function of time. Other than that, this looks exactly like what we had on the previous slide. So that means that CA could start out, say 1, CB could start out 0. They could evolve in time, and eventually CA would be a half and CB would be a half. So there'd be a change in probability, or a flow of probability from state A to state B, because these depend on time. So our goal is to find CA and CB as functions of time, and to look at C, because those can represent transitions between the states psi A and psi B. Okay, so with some work with the Schrödinger equation, and I'm going to ask you to see the text on this because it's a couple pages, but we arrive at the relationships, the following relationships for CA and CB as functions of times. They're differential equations. So this dot means the time derivative. So CA dot is minus I over H bar CA. Remember, CA is a function of time, times this matrix element, which I'll define in just a second, plus CB times another matrix element, times this exponential here. Similar equation for CB. The time derivative of CB is minus I over H bar. CB is a function of time, HBB plus CA HBA e to the I EB minus EAT over H bar. So these equations are symmetric between B and A, as you might expect, since we could exchange B and A here, and we'd have the same form of the wave function. So what are these HBB prime? Well, they're matrix elements of the time-dependent perturbation H prime between states psi I and psi j. So for example, HAA prime would be psi A matrix element of between psi A, H prime, psi A. And AB prime would be psi A, H prime, psi B, etc. Okay, so in most cases of interest, actually, it turns out that the diagonal, or the matrix elements with the same wave function on both sides turn out to be 0. Not absolutely always the case, but it's the case in most cases of interest, including most of the radiation problems. So it's worthwhile, we're going to specialize to that case where HAA is equal to 0 and HBB is equal to 0. That'll simplify our equation somewhat, enable us to make some more progress in analyzing what's going on. So if that's the case, then this term drops out. This term drops out. We get minus CA dot is minus I over H bar, H prime AB, e to the minus, okay, we're going to call omega naught EB minus EA over H bar. So that's the angular frequency associated with the energy difference between state B and state A. we're assuming state B is a higher energy than state A here. So this is a positive number. So omega naught is positive. So we have e to the minus I omega naught t, and then here's the CB. The second equation becomes CB dot equals minus I over H bar HBA prime e to the I. Now just here it's omega naught because there's no minus sign here, T, and then CA. Okay, so these are the two equations, assuming that the matrix elements, these two matrix elements are zero. So you can see that's pretty nice compact equations. So we have a chance at making some progress on these. Again, this is exact. We haven't assumed that the perturbation is small yet, but we also haven't solved anything yet. So let's look at the two-level system approximately with a small perturbation, a time-dependent perturbation. So we assume that H prime of t, the time-dependent perturbation, is small compared to the original Hamiltonian H0. And if we do that, we can solve via approximations. So we'll start in the lower energy state. So Ca at time 0 is 1, meaning it starts out in the psi A state at time 0. Cb at time 0 is 0. So it's completely in the psi A state, the lower energy state at time 0. So we're going to do an approximation to 0th, first order, and second order. So 0th order, we just have Ca to 0th order of t equal 1, Cb to 0th order t equals 0. So just what we had here. So the 0th order, it's as if we have no perturbation, no time-dependent perturbation at all. It just stays in the state A forever, no chance of transitioning to B. Okay, but to first order, we do get some changes. So using these two equations here, by plugging in, let's see, the 0th order into this. So if we plug in Cb equals 0 here, we get Ca dot equal to 0. So that means Ca doesn't change. So Ca stays equal to 1. It starts at 1, it stays equal to 1 to first order. And then Cb, we plug in Ca equal 1. So we'd have Cb dot equal minus I over H bar HBA prime e to the I omega t times 1. So to get, we can just integrate that directly to get Cb, which is what we've done here. We've integrated minus I over H bar integral from 0 to t HBA t prime e to the I omega t prime dt. So we've just plugged in the 0th order for Ca here and Cb here. And then that gives to first order Ca equal 1 and Cb equal this integral. So that's first order. Applying this again, so taking Ca1 equal 1 and putting it into to this again, just gives back the same equation for Cb that we had before. So Cb to second order here is the same as Cb to first order. So there's no change in Cb. However, putting in Cb to first order into this equation for Ca dot gives a very long, a rather long equation involving, so if we plug in the Cb1 here, we get a minus I H bar HAB e to the minus I omega t, then another minus I H bar I over H bar times this integral here. So then we can integrate that and we get a double integral. And then the coefficient, the constant of integration is 1. And we get this expression here for Ca to second order. Okay, so so we have a first order, so to first order, 0th order and first order Ca equal 1, but to second order Ca starts to lose some probability. So there's a transition, a chance for a transition, a loss of probability from Ca to Cb. And to first order, we can see, well, to both first and second order in Cb, we can see that probability appearing here. So CB can be non-zero to first and second order. Okay, there's a couple of sort of interesting interpretations of this of these expressions. So if we take the first order expression for CB, we can rewrite it. We just multiply both sides of it by e to the minus I EBT over H bar, the wiggling factor for psi B. And if we do that, we get this expression here. If we expand out omega naught equal EB minus EA over H bar and distribute things out and rearrange a little bit, we get this expression here. This has an interesting interpretation. So if we look at this, we have, reading from right to left, we have the evolution operator in state A, e to the minus I EAT over H bar, and then up until T prime. And then at T prime, we have this switch from A to B. So this switches states from A to B at time T prime. And then from T prime to T, it evolves in state B. And then we integrate over all possible times T prime that it might switch from A to B. So that's kind of an interesting interpretation of this first order of this transition of probability into CB, that it can happen at the switch from A to B can happen at a succession of times anywhere from 0 to T. And this is how we add it up. We can also rewrite the second order equation by multiplying this equation here by e to the minus IT EAT over H bar, since this is the A state. And we get this term here, 1 just multiplied by this just gives this term. And then we take this and distribute it through this expression here, expand out the omega naughts, group some terms. Not going to get into the nitty gritty details here, but you can pause and check if you want that this, when expanded out and multiplied by e to the minus AT over H bar, gives what's shown here. Anyway, what we can see is that there's two processes here. One is that the e to the minus IAT over H bar here means that the probability just evolves in state A. So that's the case where there's no transition. Now this one right here, if we read again from right to left, we go, we evolve for a while in state A using the e to the minus IAT double prime over H bar. Then we switch from A to B at time T double prime. Then we evolve from in state A to time T prime, at state B to time T prime, and then we switch back to state A at time T prime and evolve the rest of the way to T at time T prime to T. So we actually get to second order here, we have switching from A to B and then back to state A included in this, the probability for state A. So you can either, the chance of being in A can either be just stay in A or switch from A to B and back to A. Whereas when we rewrote this one, the chance to go to B is just to start in A and switch to B. Okay, which makes sense. We're either going to be in B, we're either going to, we start in A, we're going to switch from A to B. To be in A, we're either going to stay in A or go from A to B back to A. Again, to second order. Okay, so we have some nice expressions here, which we can use. These expressions here and these first order and second order expressions we can use for particular time-dependent potentials and get transition probabilities and so forth. So we'll look at one example, a sinusoidal perturbation. And again, as I mentioned, I think this is maybe the third time we've said this in this video. This is motivated by an electromagnetic wave, shown here, with magnetic fields and electric fields. Those magnetic and electric fields carry energy, which it can deliver to an atom. And there's a sinusoidal dependence of the field on time as the electromagnetic wave passes. So that's why a sinusoidal perturbation would be interesting. So we could have our perturbation H prime of R and T be V of R. So it can depend on space, but then it would be a sinusoidal, or in this case, it's written as a cosine, but it's sinusoidal of omega times t, a driving frequency, or the frequency of the electromagnetic wave is omega. And then the matrix element HAB of the perturbation would be VAB cosine omega t, because the cosine omega t, the matrix element only involves an integral over space. So that would be this matrix element here, psi A, V, psi B, which gives VAB, and then times the sinusoidal, or the cosine of omega t here. Okay, so if we use our expression to first order for the transition to from state A to state B that we looked at on the previous slide, that was given here, and assuming that if we make an assumption that omega, the frequency of the sinusoidal perturbation, is close to omega naught, where omega naught is the difference in the frequency, angular frequency associated with the difference in the energy levels of B and A. And that makes sense, because to appreciably drive a transition between state A and B, we need to have the frequency match pretty closely to the frequency of the transition. Anyhow, with that assumption, you can show in several lines, you can see the text for this, that CB of t becomes the following. If we put in this for HBA, VAB cosine omega t, e to the I omega naught t prime dt, and do the integral. It becomes minus I VBA over h bar, sine of omega naught minus omega, t over 2, omega naught minus omega in the denominator, and then this exponential here. So that's the actual CB. What we're really interested in is the amplitude squared of that, because that's the probability. So the transition probability to switch from state A to state B would be given by, since we start out with CB equals 0, so any CB is coming from a switch from state A, would be CB squared, or the amplitude squared. So this minus I would drop out. We'd have VAB squared over h bar squared, sine squared of omega. So we're squaring everything. Sine squared of omega naught minus omega t over 2 over omega naught minus omega squared. And then this, since this is the amplitude, this would be this times its complex conjugate. So this would go away. So this is an interesting expression. It depends on the strength of the perturbation, the square of this perturbation. So the stronger the potential, time-dependent potential we have, the amplitude of it, the stronger, the more likely we are to drive the transition. But notice the behavior here. It goes as the sine squared of something involving t. So it's actually going to oscillate in time. And you can see that here. The amplitude of it would be VAB over h bar omega naught minus omega squared. But the sine squared gives us this oscillation with a period of 2 pi over omega naught minus omega. If you work it out from this expression here, this will repeat every 2 pi over omega naught minus omega. So the transition probability P of t from A to B rises to a maximum, decreases back down. So it goes back. If you measured at this time, the system would definitely be in state A. Here again, it would be more likely to be in state B, here again, here definitely in state A, etc., back and forth. So very interesting oscillatory behavior. Oscillations are pretty typical of quantum systems, especially being driven by a sinusoidal wave. So, but anyway, that's interesting. And the last thing we can look at is the peak as a function of omega, as a function of omega, the driving frequency. So here's omega naught, the frequency, angular frequency associated with the transition from state A to state B. So as we get the highest probability of transition if omega is equal to omega naught. So if we drive it right at the peak, right at that frequency, angular frequency, we get the highest probability peak in this oscillating curve here. And as we move away from it, we fall away from that. So this is a graph of this function here, VAB over omega naught minus omega squared. So it oscillates around like this. Okay, so that's pretty interesting. So just a brief summary, what have we looked at? We looked at time-dependent perturbations here. Why do we look at time-dependent perturbations? Because that's the only way, if we have a time-independent system, the probabilities of the different eigenstates are fixed. And so we can't get any transitions between eigenstates. And we know there's very important physical effects like transitions between atomic energy levels, which release photons and are a big part of atomic and solid state physics that need to be described. So to do that, we looked at a two-level system just to keep things simple. We first solved it exactly, getting some relationships for the CA and CB, the derivatives of CA and CB. Then we looked for where the perturbation was small, and we looked at zeroth, first, and second order. And then and we saw that there to first order, there was a chance to switch from A to B, from state A to state B. And that was given by this expression here. And then we looked at sinusoidal perturbations because those are particularly interesting. And we saw that there is an oscillating transition probability between the two states. So there's a chance, there's an actual change in the probability of the different states, starting with 0 chance in state B, going up to a peak of a high chance of state B and back down and so forth. And then we saw how to drive a transition between two states. It makes sense to drive as close to the angular frequency of the difference in energies as you can. Okay. All right. I hope this gives you some insight into the reason why we're interested in time-dependent perturbation theory and an example, and beginning to get acquainted with some of the important expressions there. Thanks for your attention, and I'll see you in class.